The quest for life beyond Earth often leads us to exoplanets, especially those nestled within their star's habitable zone. While the fundamental principles of life might remain consistent, its specific manifestations on these distant worlds would likely diverge dramatically from our own. The unique conditions of each planet would sculpt evolution in ways we can only begin to hypothesize. The type of star a planet orbits is arguably the most critical factor influencing the development and appearance of life. Different stellar energies dictate the available light spectrum and planetary dynamics. This stellar influence shapes everything from plant coloration to atmospheric conditions. Red dwarfs, the most common stars in our galaxy, present a unique challenge. Planets orbiting them must be extremely close to stay warm, leading to a phenomenon called tidal locking. One side perpetually faces the star, while the other remains in eternal night. Life on such a world would likely thrive in the perpetual twilight zone between these extremes. Plants, or their alien equivalents, might adapt to absorb red and infrared light, potentially appearing black or deep crimson. Their biochemistry would be finely tuned to this specific energy input. Sun-like stars, classified as G-class, offer conditions more familiar to us. Their stable energy output and moderate lifespans favor the development of photosynthesis as we understand it. This stellar type provides a broad spectrum of light, conducive to diverse biological processes. In contrast, hot, massive O and B-class stars burn through their fuel rapidly. Their lifespans are often too short for complex life to evolve. Even if rudimentary life could form, the star would likely explode in a supernova long before advanced organisms had a chance to emerge. Evolution on an exoplanet would drive radical adaptations, shaping organisms in response to their environment. Atmospheric density, gravity, and even the color of starlight would dictate biological forms. These pressures would lead to truly alien anatomies and physiologies. A denser atmosphere could give rise to creatures with expansive wings or sails, allowing them to glide effortlessly through the thick air. Flight would require less energy, potentially leading to a proliferation of aerial life forms. Conversely, a thinner atmosphere would necessitate larger lungs or highly efficient oxygen uptake mechanisms. Gravity also plays a profound role in shaping life. On planets with stronger gravity, organisms would likely be shorter and more compact. They might possess multiple limbs for better weight distribution, resembling Earth's insects or arachnids. Trees and plants would need exceptionally sturdy trunks to withstand the increased downward pull. Conversely, weaker gravity could allow for towering, slender limbs or enormous wings. Creatures might grow to immense sizes, unconstrained by the gravitational forces that limit growth on Earth. Their skeletal structures would be lighter and more delicate. The dominant color of plant life would directly correlate with the host star's light spectrum. As seen with red dwarfs, plants might appear dark to maximize light absorption. On planets orbiting bright, blue stars, plants could evolve to be black, absorbing the entire visible spectrum for energy. Beyond physical form, biochemistry itself could differ. While water is considered the most likely solvent for life, other possibilities exist. Some theories propose life based on silicon instead of carbon, forming complex molecules with different properties. Even with Earth-like conditions, the planet's fundamental cycles would profoundly impact life. The rotation speed, axial tilt, and geological activity all contribute to the environment's stability and habitability. These factors dictate the rhythm of life on a world. The length of a day, determined by the planet's rotation, would influence metabolic and sleep cycles. Extremely short or long days would require significant biological adaptations. Organisms would need to synchronize their internal clocks with these unique temporal rhythms. A greater axial tilt than Earth's would result in more extreme seasons. Life would need robust mechanisms to survive vast temperature fluctuations, such as hibernation or migration. Adaptability to dramatic environmental shifts would be paramount for survival. The presence of plate tectonics and volcanism is considered crucial for long-term climate stability. These geological processes recycle carbon dioxide, maintaining a balanced carbon cycle. Without them, a planet could succumb to runaway greenhouse effects or become a frozen wasteland. In summary, while life is expected to adapt to any given conditions, its specific forms and functions would likely be utterly beyond our current imagination. Evolution, driven by billions of unique decisions and environmental pressures, would sculpt biologies fundamentally different from anything found on Earth.